Welcome to this webinar. We're excited to discuss Bayesian and multi-state models, Bayesian survival and multi-state models. We're going to be presenting content from a package that we've just released. It's an early beta package, and so we really want to hear from you what's helpful, what's confusing, how it would be useful in your own work. And so we're kind of, really excited to see how this can be used in practice. So I'm going to share my screen. Hang on one second. And I think there's a link to a POSIT cloud environment that people can see. Hopefully you're able to see that. And while you're getting connected, we have a couple things just to start us out. So let me know if you can see. Let's test.
Looking great.
All right, awesome. So just to level set, we wanted to get an idea of where people have experience and what your background is. And this will help us to tailor the content and kind of speak to what's familiar to you and what your knowledge is. So in order to answer these questions, I'm going to ask if you can type into the chat, and we'll sort of quickly monitor what the level of experience is in the room. So the first question is how much experience you have with Bayesian statistics. And this, again, is to help us kind of tailor our explanations to the level of knowledge in the room. The next question has to do with survival analysis. So the question is how comfortable you are with survival analysis, because the content will kind of build on this as a foundation, and this will help us sort of just make sure we describe the right features of survival. All right, and the third has to do with your R programming confidence. So hopefully, if you're in this tutorial, you're somewhat familiar with R, but perhaps not. There's a formatting. So C is here. That's the first intro warm up. The main reason we want this also is so we can tailor the content, but also to give you a chance to connect to the POSIT cloud instance and see if people are set up.
The task for which we developed this package initially was for dosing decisions, personalized dosing decisions, and the multi-state modeling comes in so that we are able to predict risks about different events. And this dosing problem depends on, so for example, an anticoagulant drug can cause a higher risk for other adverse events, and low risk for other events, so hemorrhagic, ischemic events, and then the patients can die or get a disability, and they can have different preferences for these events, and we want to find the optimal dose. And we can include patient preferences so that we can weight different events. This is not so relevant for this session. We would select the dose that maximizes utility, which is based on the event risk and patient preference. And the event risks depend on dose and other patient characteristics. The utility would be computed using this formula. But again, I will move on to the event risk prediction, which is just a key part of this session. So we assume that we have data where we have observed events like adverse events for some people who are on a drug, or they might be just progressing in some disease, getting more severe versions of a disease. So for these events are marked, and we will go in the notebook later through an example where we can understand this better. But we would fit some time to event model to estimate the probabilities of different events. And this is in the package that we're going to present. It's based on the proportional hazard assumption of a so in a single transition model, the basic Cox-PH model, we would have this hazard function. We have baseline hazard, and we multiply it by the proportional hazard multiplier. So this can be viewed as a multi-state model with two states. So we have the alive state and dead state. Then there's a hazard function for that one transition. So the next step would be an illness-death model where we go from healthy to diseased to dead, or we can go from healthy to death directly. And in a multi-state model, the hazards of different transitions, they are competing. So if one of them occurs, then the other one cannot occur. And the hazards are modeled like this, so we have different baseline hazards for the different transitions. So here we have three of them. And each baseline hazard is modeled using splines in the package that we will present, and then we have the covariate effects beta, and they are common. So in the BM state package, for example, since these lambda2 and lambda3, these hazards are transitions which end up in the same state. So the covariate effects are shared for those that end up in the same state. We use the Markov assumption. So the time is the time from start of study. It could be done in a different way, where time would be time since entering current state. Here's another larger multi-state model with 7 transitions and 4 states. If we have some sort of events that are not directly describing a state, like stroke or a bleed, then we can sort of artificially create a state which is based on the most recent event. And the state paths that are observed could look something like this. So we have a follow-up, and then they either get a terminal event, like dead here, and or they can be centered. So we're assuming right-centered data. Or the package can handle only right-centered or exactly observed data. So the first step is that we need to get the data into a format that consists of states paths. We will look at this format more in a bit. And then on each interval, these state transitions split the timeline into intervals, and we know on each interval we know what state the patient was in and what transitions were at risk. The likelihood will look something like this. And the key thing here is that there's an integral. We need to integrate the baseline hazard or the transition hazard. We need to integrate, and we do it numerically in the package. And then finally, about how we predict these event risks. So in the simplest case, the model is a continuous Markov model, and no loops here means like no self loops from starting state A to state A back, for example. So there are going to be other types of loops in the model. So if we have this type of multi-state model, which we which is the type we're looking at today, then we can solve all of the transition probabilities by defining the generator matrix and transition probability matrix. Jackie, I think there are some comments in the chat, but should I address those? Are they for me?
Yeah, the question is around a link to the slides, if it can be shared. And we will be sharing a link.
So the slides are in our GitHub repo, but I don't think that material is copied to the R cloud session.
But yeah, we will be sharing them. This intro set is different from the worked examples, but the repo will include all of them.
Yeah, and we can also generate paths. We can look at this also. We can generate paths according to the process to estimate the event risk. So that we just look at how many of the paths had that event state transition. Yeah, there are some challenges, but I think we need to go forward now to the actual content. So this file now is in POSIT Cloud, or probably the most recent version of this isn't there, but basically the same analysis file is there. And the first thing that probably will take some time. So Jackie, do you think do they need to install CMSD stan-R separately on their copy?
These are all installed right now. So it's worth checking that it's installed for you, but it should be installed.
Yeah, I mean because CMD stan-R is a package which is installed, but is also like CMD stan installed. I tried the cloud environment. I needed to install it myself there, but
okay. So yeah, I'm seeing people do need to reinstall it. I'm not as familiar with how the analysis setup works, so that's good.
And then this is the package that we will be using. So hopefully people have it, and I will we will go through like how we can debug the stan and CMD stan-R if that doesn't work. But first, so we will go through some data here, and during that time you should try to start this CMD stan-R install. It takes maybe a minute or two. And so this data is this cardiac allograft vasculopathy dataset, which is in the MSM package, which you should also have. Okay. I need to yeah, this is the data, and first of all, we will format this a bit because this is now snapshot data we have. So we have a lot of patients, like 500 something patients. They are observed at different time points, but they can be either in a state where they have not had the CAV, or have had mild, or have had a severe, or they are dead. And here's a link to another analysis of the data, but using the MSM package, but now we'll reanalyze it with the BM-state package. Yeah, so basically we have the 4 states here, which are no cav, mild cav, severe, and dead. These we have observed age and then the donor age. So these are transplants. So this is the donor age, and the years is the time since they got the transplant. Then there's sex also, and age, and we use the minimum age here. So the package doesn't support covariates that change over time. So we use the age during transplant. So this is the and this cumulative maximum is we're sort of taking the most severe state that it has been observed at any given time. This is what we get after the first step. And next, we want to take into account that we have observed the snapshot data, but we make a simplifying assumption that the state transition happen exactly at the first time the new state is seen. So for example here, so this person stays in state 2 for all of these rows, but we only need to take this row here. This is the first. We assume that this is the transition time to this state. So really, this data is in interval censored, but we simplify it so that we would assume the transition times exactly. There, I see a lot of things in the chat, a lot of messages.
Yeah, one of the questions, Juho, is if we can describe the state transition graph for this example, which I think you have coming up.
Yeah, it is coming up.
Mm-hmm.
So basically this is the part where we're just formatting the data into format where we only have the state changes there that we need. And then here, this is the transition matrix. So this is built into the package. You could plot this. So here you see in this graph the state transitions. So from healthy, we can go to mild, severe, or dead. From mild, we can go to dead or severe. And from severe to dead. So this is the binary matrix representing it. You could set your own transition matrix for different data using one of these functions. So for example, the survival and illness death are built in. But now the key format for data in this package is the path data class. So this helper function formats your data into this format that the package uses. And this has some useful methods. this would plot the path in this kind of stepwise plot. It's kind of messy, so it's not very useful to look at that. This is the state, transition frequencies that are observed. What else methods are there? Number of paths. In this case, the number of paths equals the number of subjects. And so the next step that you want to do before we start analyzing this data, because we use stan to fit the models. So you should be able to compile the stan model. And in this environment, you may need to set the force recompile to true. And another thing is that we need to expose the standard functions to R. These are things that are done internally by the package, but in this environment, you can check whether it works by explicitly exposing the standard functions already here. So you can try if they work. And these compilations, they take some time. Yeah, so now, for example, this is just a test function that does it work? Now this is the stan model, and you could see the stan model code here. If you wanted to edit some of the priors, for example, they're now currently hard-coded there. You would need to edit these and then set your file path to your own model. But all of these steps on your own computer, you wouldn't really need to do if everything works. This is just to confirm here that you can get this working on this environment. So should we stop here to see if people can compile the model and expose the standard functions?
Yeah, I wonder if this is a good time to pause and ask if anyone needs help with the environment or questions about what we've covered so far. So in case people joined late, we're working on the CAV example that's in the POSIT cloud environment. And there's an assignment there that you can copy and work on your own. And this is kind of a canonical example of multi-state data that's frequently used to demonstrate the methods that are here implemented.
Yeah, so by this point, you should have gotten to the point where you have created the path data out of the raw data and tested whether you can compile the stan model and expose the stan functions. Yeah, so so that comment that Jackie posted, that will install CMD stan, but if you don't have CMD stan R, then you also need to install that first. Yes, this line should work for that. So just to make clear, so CMD stan R is a wrapper for the command line tool cmd-stan. Yeah, cmd-stan R should already be there. Yeah, so someone has this error.
Yeah. So I don't actually know if our .r profile was copied over in the assignment, but it should address any issues with the exposed stand functions. So this warning that you're seeing is normal. This thing about sundials.
And the so the R profile doesn't address them completely, because I also tried this and got the same error, but then when I set force recompile true, then in that case it worked.
Mm-hmm.
But
Yeah,
I wonder
this is a warning. It's not an error, so I think it's okay.
Okay, so this is just a warning.
Yeah.
So can anyone confirm in the chat whether they were able to expose the standard functions?
We're seeing a message that it needs to rebuild command stand.
Yeah, so it will be this line.
So Juho, I don't know if you see this error on the source CPP. This might be the TBB issue.
Should I try to run it here?
Yeah, the interesting thing is that we had configured this environment to solve some of these issues, and it looks like when the assignment gets copied, not all of those solutions get copied over. So if people are running into this issue on the assignment, then we have to post the solution that my guess is that it's in some private file that doesn't get shared in the assignment getting copied over.
So I was able to run this earlier, but so at least your cmd-stan installation, it won't be copied. Like here, this is like fresh session here. I need to install this. Then usually the solutions that I do would be to just clear the workspace and restart the R session.
So a lot of the issue that we're seeing here is because the POSIT cloud environment is has certain system packages installed that may address some of these issues. If that are not installed, that if they were installed would be addressed locally. So I just want to confirm, this is the one where it says something about it doesn't find LTBB just before the error. Let's see. It's interesting because, yeah, this is the one, cannot find LTBB. So if anyone can check whether they have this our profile .r profile file in the.
Well, it is here.
It is here, right?
But I don't think this is the thing that solves it. I think there's an old executable somewhere.
My guess is that our profile needs to be sourced after command stand is installed.
So does it get sourced when you restart our session?
I think so, yeah.
Yes, the way I got this to work at least was So I clear the workspace, then I restart our session. So now, for example, it says model executable is up to date. So this shouldn't happen because it should not use the old executable. So in this case, now you should use this version that I had posted to fix that. When you compile Stan model, you you're forced to recompile.
So just to recap, I think what you're saying is if we restart the R session, it should work, or is that the...
No, because now So I opened a fresh session, installed CMD Stan R, but somehow it had the executable somewhere. It shouldn't have that old executable, so that's why you need to set force recompile to true.
Okay. Yeah, it looks like the sourcing the .r profile file addressed the issue for at least one of our participants. So this is a good progress.
Okay, now. Yeah, so this is what you should get. These are just messages from.
Yep.
Okay, so do I need to also source somehow explicitly this?
Yeah. Fun with cloud environments and Stan. There's a question here about using rstan versus command stan R. And here, I think there are two considerations. One is that rstan is often a couple versions behind the most recent version of command stan. So by using command stan R, we're able to kind of keep up to date. And the second thing here is that if TBB, the development TBB were installed on the system, then a lot of these issues would be resolved. This issue that we're seeing here is about like dynamically linking to finding the right version of this. So it's installed here. And we just have to kind of make sure that the RCPP can find the right location for that file.
Yeah, this package uses CMD Stan R. It's not possible to switch it to rstan here.
Yeah.
I also wonder why does the compilation take so long here on the cloud?
Yeah, command stan R does limit us right now from submitting to CRAN. I think if this is a blocker, then in the future we could consider changing, like pre-compiling the model. There's a single model here. So it wouldn't be awful to recompile it in much the same way that rstan-arm does. But right now, using command stan R actually gives us some flexibility in other parts of the stack that we're using. That, you know, it also allows us to keep up to date with the most recent versions of command stan. So this is somewhat of a design decision, but open to feedback on that.
Yeah, right now I don't think I can get it to work. Should I just go through it on my own computer?
Yeah, I think go through it on your own computer and
yeah. So I think it's cleaner if we look at this rendered version. So this is the data analysis. Now, if we get here, then this is the part where we create the model. So we use this create MSM function, which is calling this initializer for this multistate model class. And here we set the maximum time that we're interested in. We actually set it again here. But this is the number of integration grid points. We don't really need to talk about that, the effect of that now, but it affects the accuracy of the numerical integration. Then well, first of all, we need to give the transition matrix and the covariates for the model. So in this case, the covariates are age, disease age, donor age, and sex. And this way, this is the function that we use to set the spline knots. So these are the spline knots for the baseline hazard splines. If you don't know about splines, they are sort of basis functions that are based on certain locations, and then it's the sum of those that is the modeled hazard, baseline hazard. So this PD transition times, it gets us the times when transitions occurred. So these are years, and we set the knots. This function sets the knots based on the quantiles. I think this is a quite common technique in survival analysis to set the knots based on quantiles of the event times. And now we get 3 knots. The default was 5. Now we set them 3 knots. We could see where they go if I put 4 here. But let's do 3. So it's just the start point, the end point, and then 1 at like 5 years. Now, when fitting the model, this would ideally be done with the sampling method where we MC sample parameters, but now we just optimized them because it's faster, but this gives us the maximum a posteriori point estimate of the parameters. If it converges, there's no guarantees that it finds the maximum, but for a fast demonstration, this is now the way how we get some parameters fit. And now we get the multistate model fit object. Which has some useful methods.
Sorry, there's a question about the splines, what kind of splines they are.
Yeah, so they are B splines.
They're B splines, correct. Yeah.
Actually, I can plot them here. Now, so this seems to have 4. So let's see if I set 5. And yeah, so these are the knots. There are now 6. So apparently this argument is actually 1 minus the actual basis functions that are they're computed using this splines 2 package and using B splines. I should check that why is the number of those basis functions 1 plus number of knots. But this is the locations that it's getting, and we can refit this. So one interesting thing to look at is the baseline hazard, different transitions. So we could plot it this way using the plot H0 method. So like the more spline knots I use, the more nonlinear these could possibly be. So if we see that the baseline hazard, for example, from severe to death, it's much higher on average than the hazard from mild to death, where it's not super much higher, but slightly higher, which we would expect that the severe CAV is sort of information that the death risk is higher, and the lowest hazard is for healthy to severe, apparently because they often go through the mild version first. And then this covariate effects method, this gets the estimated covariate effects beta. Now this is an R-var. If you don't know what R-var is, it's a distribution of draws. So we get the NA for the standard deviation here because we have only a point estimate. But so we see here, for example, the effect of age on transitions that affect death is very high. And also donor age to death is slightly, means that people who get transplants from older people there have a slightly higher risk of death, of transitions that lead to death. Okay, but then once we fit the model, what can we do with it? Well, if you remember the presentation from the beginning, we're interested in the event risks. So for a given patient, or potentially for a new patient, what is the risk of, for example, death during some time span? Now this p-state occupancy is the function that solves the probability of occupying a given state at each output time point. And now we don't give the data argument here. Z. So OOS means out of sample, so it's false here. So we computed for the subjects that were in the training data. So this computes for each subject the probability that they are in any state at given times. And this we can plot. So we see here that one line here is one subject, and the coloring is done by age. So the yellow ones are the older ones, the blue ones are the younger ones. And we see that first everyone starts healthy, and then the probability of being healthy decreases over time. And for example, the amount of people who occupy the mild state is highest around 5 to 6 to 7 years. And then basically after 15 years, almost, or let's say a very high percentage of the subjects have died. We can also group by sex and see other differences on average. So the sex difference is quite small here, but it may be relevant. And then finally the donor age. Also we see that the people with higher donor, with a donor that was older, have a slightly higher risk of death, but it's not as clear as the effect of the patient themselves. Okay, then now what we would really want to do with this model is, let's say you're a new subject who was not in the data, nothing is observed, you are getting a transplant, and you're of a certain age, then what are the probabilities that you will get a severe CAV or die during some time if you get a transplant from someone from a certain age? So here we predict the state occupancy probabilities for subjects over this sort of grid of donor ages, and we can again plot these probabilities. So if we start from healthy at time 0, we see that the older the donor age, the higher the risk of death. But what is more interesting is maybe with the multi-state model, we can do something that we couldn't directly do with a basic hazard model, is that we can start predicting what if at this time 0 we had a mild CAV already, then how do the probabilities change? And what if we started from state 3, so we had the severe CAV. So we see that if we start from severe CAV, then at 10 years there's already a very high risk of death, and it's larger for higher donor ages. And we could compare these. And okay, finally, let's go through the path generation algorithm if it's slightly more generally useful. So here if we now just do this filter, we just take the first subject that was observed in the data, well, it seems like what happened was a mild cav had been observed at 2 years, a severe one at 5 years, and then death at 5 point something years. So for this subject, we can generate 1,000 similar paths, but not using the observed data, but using just the fit. And here we're sort of treating this as an out-of-sample subject by giving the data. And now this PG has 1,000 paths generated. This plot is quite messy. But here we could again plot the transition frequencies. We see that from state severe, it almost leads to death. But this is not so informative because these depend on the entire path and the censoring that happens at the end. But what is more informative is the probability of visiting a different state, which could be computed using this function. So this was the age, and this was the donor age and sex for this patient. We see that these are the probabilities. So this doesn't have the row names, but the first one is mild, then severe, then death. So actually death risk is very high. So this the risk of this intermediate state is something that we could not compute based on just the state occupancy probability, because state occupancy probability gives us the probability of being at the given state, but we can have sort of skipped or gone out of that state. So this is the entire state visit probability. In this case, the state occupancy probabilities, I think, are enough for this data to draw our draw the inferences that we're interested in, because the multi-state model has this structure of going in one direction. We always go to more severe, to a more severe state. But if we had some sort of loops or going back to healthy, then we would probably need to use this path generation method for getting the state visit probabilities for the intermediate state. So this is just an example how it could be done. And if the paths are kind of more useful also, so that we can check the event time distribution. So this is for death. So this is just the kernel density of the death times that we generated for this subject. And it's not totally correct for estimating the expected time of death, because it doesn't take into account that it's possible that they don't die at all during this. So there's censoring, but in this case, almost the death probably during the 20 years is so high that this can almost be used to estimate that the expected death time is somewhere around the mean of this distribution. There are some exercises which I don't think have been copied to the R cloud environment, but these are some of the questions that we could answer So for a given patient, what is the death probability, or what if we observe some intermediate severe adverse event? How do the death probabilities change in that case? These are the things that we're interested in, and what the package has been built for. Now I think if you got the package working, then you can try now or later to answer some of your own questions that may have come to your mind about what you would like to predict about this sort of data. Are there interesting questions that you think the package could answer? And I don't know if we need to actually do the exercises here. I think we have taken quite a lot of time. What do you think, Jackie?
Well, no, this was great. Thank you, Juho. I think I wonder. So we have a second worked example that involves some oncology data, and I wonder if there are any questions about this, or comments or issues running the code still, which my guess is that there are, if it's worthwhile to pause and address any questions before we move on to the second example.
Yeah, but so you have your own environment working where you can run it in, right? For your part.
Mm-hmm.
Okay, so in that way, I think that will be a more useful demonstration for the exercise, and I think your part has like more of the exercises. So yeah, but we should stop here to ask questions.
Yep.
But if no one can run it on the cloud, then
I think we have some examples that ran on the cloud. First, there's a request to share the link to the cloud space again. Second, I will say that the assignment's been updated, so the latest current version of the assignment has the latest version of the code that Juho ran. And we're going to share a link to the cloud space again. I'm just looking through. And the third comment I'll make is that we've sort of consolidated the issues with command stand R and expose stand functions. So it looks like if you install command stand R and then restart your R session, everything after that should work. You may see some warning messages, but we haven't seen any errors in that case. So it looks like command stand R needs to be installed first in order for the .r profile to pick up the paths to all the companion libraries that need to be loaded. So that's kind of the latest update on the status of the cloud environment. And so what I'll say in the next example is that I'm going to walk through an analysis of some oncology data where we're going to construct the transition matrix sort of more by hand than was done here in the example that Juho shared, which is more of a canonical example. And I would say if there are any questions on this CAV example, you can post them in the chat, or you can post them on the GitHub repo that contains the source code and the latest version of this. So this is definitely something that hopefully can continue to be useful to walk through.
Yeah, it will be probably useful for people who weren't able to run this. It will be useful to run this first because this is an easier introduction to the package than the oncology example, because this has a quite simple transition matrix, and also like we are using this data which is simpler, I believe. And in this example, we didn't have any kind of dose or treatment like in the presentation that we had. This was motivated by dose selection. So this example didn't have a dose covariate, but in Jackie's example, I think there's a treatment. And we have applied these to cases where we have a dose, but currently for the public data sets that we found, we don't have dose there, but as you could imagine that the dose selection problem could be based on similar state occupancy probability calculation as is done here, but just instead of running it with different donor ages, we would run it with the different doses and see the effect on the event rates.
Okay, so I'm not seeing other questions coming up here. I think let's switch gears to the oncology example, and I have some slides to introduce this. This is based on the file slides.qmd that's in the Squire folder of the repo. The data here that we'll be analyzing is from the Squire trial, and they were shared publicly in a recent publication summarizing a Bayesian multi-state model. So very applicable to this use case that we're considering here. This is the study that was published that from which the data were taken. It's a phase 3 trial in non-small cell lung cancer. Patients were not previously treated, randomized to nicitumumab plus chemo versus chemo. And here we only have data from the control arm. So folks who've worked with oncology data will probably recognize some of the outcomes and endpoints that are analyzed here. Typically, when we actually in the package itself, it embeds a PK model to estimate exposure. So Juho made reference to a dosing question, and typically we're looking at that in the context of a pharmacokinetic analysis. Here, we're just using the control arm only, so we don't have a dose question. But you'll see that we've built in the package, there's a lot of capability to simulate data. And so what I'm going to walk through here is using this as a basis for understanding the typical transition rates among the states, and then we can simulate data based on that foundation. So the data includes a number of states for each patient. We have the initial state, which here I'll call randomization. There's a treatment response, which is based on the longitudinal SLD data. There's a disease progression indicator. There's an indicator for the censoring of progression data, an indicator for fatality, and an indicator for censoring of fatality. And in the original analysis, these two censoring events were treated as states. They were not treated as the absence of a state. And in addition, we have two baseline covariates, ECOG and time on treatment. So before we do the analysis, we're first going to reformat the data because this way of handling censoring is a little bit unusual. And also the time on treatment typically is an important indicator for potential early stopping of treatment due to toxic adverse events. So as an aside, ECOG is a score that describes the subject's health status. Higher values are much worse. This is a standard way that oncology data patients are rated in terms of severity. Most trials are limited to lower ECOG levels. This trial includes patients all the way up to ECOG of 3. So in the example, there's a function format data that prepares the data. It basically does these 3 things. I'll summarize here. The original data looks like this, where we have 3 states and days on treatment. And this is how it looks after it's transformed. So we've added the censoring time as a record with is transition false. And we've also added the state of a treatment discontinuation based on this baseline covariate. So this is kind of the summary of what the data transformation does. It's pretty minimal, but important to format for the package. These are the states as a summary that we have. We have 6 after formatting. And here I'm showing a plot of what the paths look like for example patients. So here's a sample of 10 patients. They all start at randomization. Some of them have a treatment response. And here I've colored each state based on the status at the end of that interval. This subject had a treatment discontinuation soon after response, and then progression, and then censoring is shown in gray. The fatality events are shown with blue squares. If we expand this to a larger sample of patients, we get a better sense of what the typical paths look like in this sample of data. So this is a trial of patients who are don't have a great prognosis, so the rate of fatality, unfortunately, is quite high. And the other thing we see is that the no progression time, the censoring of progression, tends to happen later in patients where their survival is longer without a terminal event. And we also see here a higher rate of response in these patients. So this data inspection, we should see this match our intuition as we go through the analysis. This is the distribution of ECOG score at baseline. So I think I mentioned that we have a handful of patients with higher levels of disability, physical disability at the beginning of the study, but the majority are in this 0 and 1 category. And now we're going to start the process of constructing the states. So if we include all 6 states, this is our full transition graph, which subjects can go from randomization to response to progression to treatment discontinuation to fatality. So any one of these states can be preceded or followed by treatment discontinuation. And otherwise, there's kind of a sequence. So you can't go from progression to response in this data set. And you can't go from no progression to progression. So certain paths are not open. But if we fit this full transition graph, we would have 17 transitions, which is quite a lot for a sample of around 500 patients. But nonetheless, for data review and inspection, it's helpful to see what these transition rates look like. So in the beginning of this example, if you walk through the fit0.r file, it'll actually generate this data. There's no model fit here. This is a summary of the observed data. And we can validate our assumptions about the typical patterns. So typically response is here, and then you can have treatment discontinuation and then fatality. And the other way to look at this is to see how the fatality rate varies according to the preceding event. So progression is obviously very bad. The absence of progression is also not a great predictor. And then treatment discontinuation. So we do have some patterns of, so it's much more common to go to progression and then treatment discontinuation than the opposite. So progression rarely follows treatment discontinuation. So you can kind of see some patterns here. And this is what the state path diagram looks like. This kind of shows the time course of events. Initially, we're going to start with a simplified event graph because fitting 17 states is probably not necessary. We're just going to fit these 4. And this would look very similar to the 4 states that Juho summarized as well, with the mild, severe CAV example. Of course, here we can see a little more clearly the typical pattern of either progressing followed by fatality or some response followed by progression. So these transition rates are important to look at. In the code, when we construct a custom transition matrix or the states, we want to, the way that I generate this is I construct the full transition matrix and then I kind of prune the transitions that are not observed. So coming back here, there's a transition from response directly to fatality that's never observed. And although theoretically that's possible, I made a decision to prune it from the full transition matrix. And in your analysis, you can decide whether to include these possible transitions that are never observed and have that be part of the baseline hazard of events that are never observed, but could theoretically happen, or remove that transition entirely and have it be something that is not even possible and would never show up in the simulated data. So here we're working with this file, and because these models can take some time to run, I typically don't embed them in the QMD when I'm fitting the model. A QMD would be working with a model that's already been fit. So that's my typical workflow at this point. Now, the use of the package, there are kind of 5 steps in order to actually start getting your samples. And I found it's helpful to organize it in this way. So you'll see in the file that I actually number the different sections with the steps that have to run. The first thing is to format the data. Then we create the transition matrix. And this is where we prune the states that we don't want to include in our model, or the transitions that we don't want to consider as being possible. We create the path data based on those transitions. We create the multi-state model that includes the transition matrix and the covariates of interest. And finally, we run MCMC samples, or you can use optimize or other, there are other alternatives here available. The stan fit command, for those who know stan, you can pass in any arguments you want to command stan r, the model sampling method. And so, for example, if you wanted to fit like a pathfinder and pass it as initial values or do anything that you would normally do with your stan model, you can do that in this same command. So here, I thought I would come back and actually walk through this example. This is what the file looks like for those who have seen it. there's this first 5 steps of reading and formatting the data. We prepare the transition matrix. And so here, we're going to take the states, we're going to construct the full transition matrix, and then we're actually just going to prune this object so that the matrix only contains the transitions that we want to be possible. And at that point, we create a new transition matrix and can plot it. And that's how this, this gets generated. Then we format as path data and create the multi-state model. And finally, we can fit it. So this fit can it takes longer on POSIT Cloud than it does on an Apple computer or a laptop, but it can take a while. The fit time will be a function of course, the number of iterations, but also the grid that you give, how many of the times that you're going to use to integrate the hazard. At the beginning of this file, you can set these, how many grid points and the iterations and how many cores. And this actually will impact the estimation time here. But this gets saved in the environment. It might have gotten copied over in your copy of the assignment. I'm not sure if it was saved. It should have been, but my testing may not match your testing, as we've seen. But for the most part, these fits, they work quite well. So even with 50 warm-up draws, 50 post-sampling draws, we have very good diagnostics and very good behavior for this model. So coming back to the slides, I want to see if there's any, if anybody needs help with this part, but the main thing we're going to do after we fit the model is use this to simulate new data. So this plot here is showing the baseline hazards for each of the transitions conditioned on the previous state. So the hazard for progression conditioned on whether you're in the randomization state or you've had a response is actually quite similar. There's a difference here of timing. The biggest impact is, of course, on the fatality risk, which is what we would expect to see. Then we can summarize the posterior estimates of our covariates on the different hazards for events. The way that this model is structured in the package, each covariate affects the event risk using a proportional hazard that's shared across all the hazards that end in this event. So all the transitions that end in progression. So these are event-specific hazards rather than transition-specific effects. And then finally, we want to estimate the probability of being in each of these states according to your baseline covariate risk. So not surprisingly, higher values of ECOG lead to higher rates of progression and fatality and lower rates of response. So the directionality here is as expected. And here we're showing a posterior median and 90% credible intervals. And finally, we'll score the model because in the examples that are given, we consider different possible state transition matrices. And a question is how well the predictive performance changes. How does it change as we modify which states are considered in the graph? This model in particular, and with only 50 draws and a pretty sparse time grid, is not much different than what you would see with a time to event model for fatality. So in the example, we walk through fitting both the multi-state model as well as a single event model. And the intermediate states don't add a lot of information to the prediction of fatality, probably because the rates of progression are quite high, and progression is very predictive of fatality. So we're not really adding a lot of information by including this transition matrix. In fact, the coefficients are very similar for both the multi-state model and the time to event model. And then even the predicted event risk survival curves are also very, very similar for the two models for each of the categories of baseline ECOG. But the point here is not to rehash things that we already know about oncology data. The goal I wanted to walk through was an example of using these estimates of the transitions across these states to simulate data and answer particular questions. So here, if we read in a fit object that's already been generated and saved, we can take the mean of those parameters for each of the parameters and use that to simulate new data. So every multi-state model has a capability of simulating data. And here we're going to use the same model from this fit to simulate data for 550 subjects with the same ECOG effect and baseline hazards as the posterior mean of our previous fit. So this kind of supports the Bayesian workflow quite nicely because we can quickly check that our model is able to recover values in a simulated data context. So the simulated data that gets generated, it's going to make reasonable assumptions about the covariates. So here it's assuming this is a categorical binary ECOG status, which for our purposes will work fine. And this is the simulated transition matrix, which matches our observed data rates quite closely. And the question that we're asking is how well we can recover the true values of the covariate effects on the hazard and the true baseline hazards. If we repeated this many times, we would get a sense of how reliable the model is for recovery of effects of interest. So this is a worked example in the code. And I can sort of quickly, let me see if I can get this to allow me to switch to my, here. So this is working through this example and fitting a model to the simulated data, and then we can test the recovery of both the true hazard effects, covariate effects, as well as the true baseline hazards. And because I'm not sure who's able to use the cloud environment at this point, I was going to just jump into the summary of the results. But it's quite a nice way to compare the estimated baseline hazard with the posterior mean true values that were used to simulate the data. And what we see is that these tend to recover quite well. And here, again, we're looking at a posterior median of the draws and the 90% credible intervals of the estimates from just 50 post-warm-up iterations. And similarly, we can look at our ability to recover covariate effects. For ECOG, for most of these, we would expect our posterior inferences to be somewhat pooled towards the prior, which would have been at 0. And in fact, here we see, even with this sample size, we can estimate the effects quite well. So next, we want to update our simulation to simulate a treatment effect. And in the model code, this is not terribly difficult to do. So the first thing we're going to do is create a model that has a covariate for treatment. And this is a copy of basically a slight modification of the previous model we had. And then we're going to simulate some treatment effects. Use this model to simulate our data.
Yeah, if you want it to run faster, you probably can use lower in the grid. It'll give you a warning if the data has very short observed time intervals. It will give you a warning that the numerical integration interval is high compared to that, but it should still be quite good because that creates a very large grid.
Yes.
Yeah.
So one thing I found is that the concordance index is quite sensitive to the grid, the number of integration points. That I don't know if that's just a fluke, but yeah, we can make this smaller. This is an argument, or this is something that's easily modified in the data in the R code example. So here, when I simulate the data, we're going to simulate a case where treatment increases the response, but has no impact on progression or fatality. And here, if you wanted to change these assumptions, you could edit the code and run it. It would update those assumptions. But the first question I was thinking about is how likely it is that a drug that improves the response rate would actually have any impact on fatality, which is the outcome that most patients are concerned with. So most of our treatments, we're looking for overall response rate or even progression-free survival. But given this setup, we can simulate data where treatment effect is pretty modest on response. And this is similar in magnitude to our ECOG at baseline, but has no direct effect on fatality. It only affects fatality through the impacting the downstream events following treatment response. So our data will now include a new field, treatment, that's randomly assigned to 0 and 1s. And we're simulating data with this hypothesized treatment effect. Our state transition graph is very similar to the one we had before. It's not going to be hugely modified. This response we would expect to go up, but the other events should be similar. And given here the kind of how common progression is, a reasonable question is whether we would expect to see any difference in overall fatality given this drug that increases the response rate. In the posterior of this model fit, we're able to recover pretty close to the true parameter estimates. And here it's going to depend a lot on the exact instantiation, which seed is used for the generated data and the quality of the fit. But all of these are within expected values for the credible intervals that are estimated. But not surprisingly, perhaps, we see the response rate is higher for subjects who are treated. And actually, progression is also oddly slightly higher for subjects who are treated. And almost no effect on overall fatality. So in summary, this is the overview for fitting a model to using this package, BM-State. And we have some additional examples here that explore results with different composition of states, transition matrices. So with that, I thought we should pause and ask if there are any questions or comments on what was presented here. So the package is currently available on GitHub. And I don't know, Juho, if you want to share a link to the BM-State package in the chat.
Okay. Also, it's just a link, but when you install GitHub, you are using this.
Thank you. This is here.
And the
And we
package
have
has also other vignettes that we didn't look at, which might be useful.
Yeah, any issues or questions here? Oh yeah, we'll share this link. Thanks.
So yeah, all priors are hard-coded currently, and they might be quite ad hoc, but as I showed, you should be able to edit the standard code and use a custom stand model. I haven't really tried it, but it should be possible. That's kind of a hack which is not guaranteed to be supported.
Yeah.
Okay, my messages were not going to everyone.
Yeah. And we'll also be releasing the code for this tutorial. I don't think it's currently public. It's only in the cloud environment, but we will be making it public shortly after this tutorial. We just need to update some of the documentation and examples. So I guess unless there are any other questions or comments, that should conclude the material for here. Yep, the cloud instance should be available going forward. Thanks.
Yes, thank you both for this very informative and very chock full of great content presentation. I really appreciate it. Don't see any questions. Oh, here's one. They're asking, how do you print stand code, by the way? Oh, they're just okay. Just asking for
Yeah,
that.
so so if you create a stand model, then the stand model has the code method. So this gets you if you created SM like with this.
I'll share.
He's saying it's after fitting. Oh yeah, and then yeah, that's yeah.
So as an example, here we have this mod 0. Can you do it on this? What's the command, Juho?
The stand model is not an object of, it's not a part of that model object, because the stand model is part of the package, and the package is assuming that there's only the one stand model.
I see.
So you can take stand, if you have a fit, you can do yeah, the fit doesn't save information from stand because
Right.
by default the package is tried to be done so that it would be possible to do another backend fitting for fitting rather than stand, but that is currently not implemented. So if you do the fit, then you need to give an argument that is explicitly saves the stand fit. Yeah, and
I
changing
have this one
it
here. Yeah.
would be tricky.
This is this one.
I can do another vignette which would be demonstrating how to use a custom prior.
So I think if you take a fit object, this is a very easy way to see the code.
Yeah, so for that you need to have given save stand fit true when fitting, but the package is currently trying to save memory by not saving the stand object by default.
Yeah, I like to keep it. I think that's my preference, but I understand that the goal of saving for sure. The model includes, you'll see the PK component as well, although it's optional. So it's only used if it's turned on and the data are provided to estimate it.
Great question. Yeah, keep them coming, guys, if you have any.
Yeah.
So
this
is a link to GitHub with where the stand model is.
Yeah, this is another way to see it quite directly.
But this package has, if you are wondering what the PK stuff there, this package has, you can also fit jointly a pharmacokinetic model and use the average steady state exposure estimated by the PK model. You can use it as a predictor. This is more of a experimental feature, but it takes a lot of the code code lines in the stand model.
This is a model that we've been using for a couple of analyses, and so as it's become more mature, I think we're looking to open source it so that it can be used more widely. Cool.
Yeah, it's great
Well,
to hear. See, I know we're
thanks for,
approaching time. Yeah, thank you guys. Really, I really appreciate you guys spending the time, especially, I'm sure I can mimic the sentiment of the rest of the organizing committee of being able to take the time to put this workshop on. Without you guys doing this, we wouldn't be here. And I really just want to say I really appreciate it. It's been super informative.
Cool.
oh, thanks for putting on the conference. It's great.
Well, I look forward to hopefully you guys can put on another one next year. No pressure.
Cool,
Uh,
thank you.
yeah. If there's no other questions, I can go ahead and close the bridge. We have one more workshop going on as we speak over Teal, and that will be the wrap up to RN Pharma for 2025. Yeah, anybody has any more last minute questions or thoughts, please get them in chat. But otherwise, the recordings will be made available after we've done our edits and gotten permissions from everybody, and that should be about typically a month, sometime by end of year. But yeah, the cloud instance will remain up for the entirety. So get your copy to your own profile. Usually, I think you have a limit of 25 or 30 of those, but that should live there in the entirety if you guys ever need to return back to that. So, all right. I guess with that, I will go ahead and close everything down. So thank you guys again.